First, let's start with a little introduction about me. My name is Jorge Morales. I'm from Spain, so that's why I have this Spanish accent. But I'm Spanish also by nature, so you'll see me probably in the party tonight. I work at Red Hat as OpenShift developer advocate, and I'm mostly a Java developer. Although I know how to program in many other languages, I will say that Java is the only one I'm a little bit proactive. And I'm obsessed with improving the developer experience, always trying to make our product more developer-friendly. These are the usual places where you can find myself, my content, and probably things about me. Let's just start. José Saramago, Portuguese, once said, each day is a little bit of history. That means that every day something happens that changes the history, changes the things as we know them, changes the things as we see them. Today, I'm gonna tell you a story about the history of containers a little bit. And like every story, it starts with once upon a time. So once upon a time, there was a technology called Linux containers. Linux container was a technology that used things from the Linux kernel. So it used kernel namespaces to provide sandboxing for the processes, so isolation between each process, between one another. It uses technologies like control groups, C groups, to provide resource allocation, resource constraint to these processes, amount of memory, CPU, I/O, network that the process could use from the operating system. And it also used things related to security. So being able to drop some capabilities to prevent privilege escalation, mandatory access control. These technologies were really tough technologies that mostly operational people used back then back then in the days. This technology was somehow similar to also virtual machines. So I got this analogy which I made when my father, which is 70 years old, he asked me, hey, what is the difference between containers and VMs? Once I start talking about what I do, like, how do you explain a 70-year-old man? What is a VM? What is a container? What is the difference? So I use this. A VM is like a house. You have a house, you get into the house, you got the walls, give you the boundaries of your house. Everything that's in the house is for you. All the resources that the house has, the water stream, the electricity, they are all for the house. The house occupies the entire ground space where the house is built. On the contrary, containers are like a building of apartments. The ground is shared between multiple apartments, and people that gets into apartment, they have the same walls as the houses, they have the same resources as they can have in a house, electricity, water, but they are shared between all of the people that live in the same building. So if you have the water tap open in one of the apartments, you get the flow of a stream, which is the flow of stream, the flow of water that is guaranteed to you. But if everybody in the apartment building open the water at the same time, probably you will not be able to get the full stream of water because this resource is shared between all the people in this building. But VMs and containers were technologies that were meant to be used by developers, but they were not really developer friendly. And developers, they wanted to do things in an easy way. Making things easy, it's hard. It's really hard. For many, many years, Linux container existed, and they were only used by very few people that they knew how to tweak all those difficult stuff that we had in the Linux operating system. But there was a company, Docker, that made things easy for the developers. They changed history the day when they released Docker. Docker no longer became, or Linux container no longer became something difficult to use from a developer point of view. Still was using the same capabilities from the Linux kernel, from the Linux operating system, to provide sandboxing and isolation for your processes. But at the same time, it was also providing a way for developers to package applications and to be able to move applications from one place to another. So from that time, developers were a little bit more happier, and they started using this technology. They started using it so much that many developers, they were creating containers for anything, almost anything. But containers were difficult to scale, to manage at the scale. So having one container, as a developer, having one container on your laptop, it's easy. You can just Docker start or Docker run. You have your container up and running, and you can do anything with it. But then when you want to run those containers in a production environment, you want to have multiple containers collaborating, talking to each other, sharing networks, sharing storage, sharing resources. There is a lot of things that become really difficult. So to that, you need some orchestration. Orchestration is a way of putting things and coordinating things together so they can collaborate, they sound like they are in harmony. The landscape for orchestration was something that has changed in the last years. Some years ago, there were multiple orchestration engines available. There was Kubernetes, there was Docker Swarm, there was Mesosphere, there was some smaller or more, not so much used orchestration engines like Cloud Foundry Diego, Nomad, Blocks, and blah, blah. But today, we see how the landscape has changed, and most of the people has bet on Kubernetes. So Kubernetes has become the de facto standard for running containers. Still, the other containers are still there. The other container runtimes orchestration engines are there, but they are not so widely used. Why Kubernetes? So one of the reasons why Kubernetes became the de facto standard was the community. Open source, it was a community, big, vibrant, open source, and backed by giants. So Kubernetes was a project started by Google based on the knowledge they had by managing and running containers internally in their data centers for many, many years. But many others are backing up Kubernetes right now. So there is a lot of contributions to Kubernetes from companies like Red Hat, companies like IBM, companies like, of course, Google, Oracle, Amazon Web Services, Microsoft, and many, many others. It's supported on all clouds, so you can use Kubernetes almost anywhere you want. And it has great partnerships. That means that there is a big ecosystem of technologies that will integrate with Kubernetes very well. So if you bet on Kubernetes as orchestration engine, you want to have a lot of, or everything you need available. So how the history goes with the container orchestration engines. Back in 2014, Docker 1.0 made the first release. And in July 2015, 1 year later, Kubernetes released the first, shipped the first release. In the meantime, there was some other container engines like Rocket, which in December 2014, they were in the release 0.1. After that, in February, Rocket became, or released the version 1, and people start liking the technology. There was some differences between how things work in Kubernetes, or in Docker, and how things work in Rocket, and there was some people advocating that Rocket was doing the things in a more technically advanced way. So Kubernetes decided to start supporting both container runtimes, Docker and Rocket. But as you can guess, being developers, when you don't expect that you are going to eventually support multiple things, you start doing a lot of if-elses, switches, conditionals in your code. So it becomes a little bit of spaghetti code. You want to support Docker and Rocket, but what happens if you want to support more? So sometimes you need to slow down, stop, and think, that you need to change some things that you have done up to that point. Two things happen related with this technology. One of them was that Docker and the people, the ecosystem around Docker, they pushed the company to try to standardize the technology they were using. Why? Because they were doing a lot of tools. They were building a big ecosystem around Docker, and they were fearing that a company that was private could probably at some point in time go in a different way. So they pushed Docker to try to standardize the formats. So once the way the containers were run or were defined, the ecosystem could potentially grow without fear that things would change. So the Open Container Initiative, although it was formed in 2015, Docker and some others didn't still adhere or change the code until 1 year later. So what happened is Docker donated their code, the internal how they run and how they define the container image format as the initial specifications. There was two specifications, one the runtime specification, how you run containers, and there was a reference implementation called runc, and that is the code base of more or less Docker. So then afterwards, Docker changed their code to run with runc. And then the image specification. The image specification is really important because it defines how you are going to be creating an image. An image is a transportable file that you can move from one place to another. Developers were using images to put their application in images. So it was really important to know that if I create an image with one tool and I give that image that I have created to somebody else that will use a different tool, it will still be able to use it and understand it. There is another proposal now ongoing in that OCI, the Open Container Initiative. Another interesting thing happened at the same time, more or less, and it was that, as I said, Kubernetes, it was using a lot of conditionals in the code. If Docker do this, if Rocket do that. So they decided to go with what the Java developers have been saying for a long time, use interfaces, abstract everything away from using interfaces. So they created something called Container Runtime Interface, CRI, to abstract away how you can run containers, how containers are run. So the kubelet, which is the daemon that in Kubernetes acts as acts to run containers, it only needed to talk to this interface, and then multiple different implementations just were behind this interface. So you can have Docker, you can have Rocket, but there is some other interfaces, but also some other implementations back there. So standardization became a fact. That means that in Kubernetes 1.5, CRI became alpha, and in Kubernetes 1.7, July 2017, Kubernetes CRI CRI became GA in Kubernetes. What is the container runtime interface? It is nothing more than an interface. We're using a gRPC interface between the kubelet and little adapters called shims that act, or that every container runtime will provide. So every runtime will provide a little shim that will know how to translate from this CRI, this container runtime interface, into the specific way of how they run the containers. So there is a CRI shim that translates from CRI to Docker, which is the Docker shim. There is one for Rocket, the Rocket shim. And there is many implementations, and more are coming out. If you look into the implementations that we have, CRI-O, Containerd, Docker shim, Rocket-led, they run containers. But there is also two there in the picture, Fracti and Buildah, which using the same interface, CRI, Container Runtime Interface, they run VMs. So they allow you to run containers inside a VM. CRI-O. CRI-O is the topic of today's talk. One of the topics. So what is CRI-O? CRI-O is an open source, an open governance project. It is hosted under the Kubernetes incubator repository, GitHub repository, and it's a lean, stable, secure, and most importantly, a boring project. Why is it boring? Because it's just tied to the CRI. That means that there is no other features that it will implement that can mine stability or performance. There is nothing more that they will do. CRI-O is only meant to run containers for Kubernetes. It's shaped around Kubernetes, and it's the only supported user is Kubernetes, and of course any other Kubernetes implementation or vendor like Red Hat OpenShift. And the versioning and support is bound to Kubernetes. That means that every time Kubernetes creates a release, there is a release of CRI-O. So Kubernetes 1.9 has CRI-O 1.9, Kubernetes 1.10 has CRI-O 1.10, and every time there is a patch release for Kubernetes, there is a patch release for CRI-O. Okay, so now I think it's time for a little demo. Okay, here as you can see, I have done Docker images. I don't have any images on this environment. I just connected to a VM in my laptop, so we can do kubectl get nodes, and you see that I have one VM running on that IP, which is running Kubernetes 1.9.1, and it's running on my laptop, and it's acting as a master and as a node in Kubernetes. Docker doesn't have any image, but still Kubernetes is up and running. Let's even stop Docker. So as you can see right now, I cannot connect to Docker, but I'm going to deploy containers and images in Kubernetes. So right now, I don't have any pod in this project, in this namespace. What I'm going to do is I'm going to run one nginx server. So kubectl run nginx --image nginx, and I'm going to use port 80 for accessing my application. I've created one pod. To be honest, really what this created is not only a pod, it created a deployment in Kubernetes, but the deployment only has one instance. It's scaled to 1, so that's why you see only one pod. It's running, the pod it's running, but it doesn't have Docker. So let's see if really things are running. kubectl, let's expose the deployment. Okay, and kubectl get service. Here we have a service, and let's verify curl HTTP that I can access that pod in the port 80, which is by default. So you see the default response from nginx. This is running OpenShift, which is the Kubernetes distribution by Red Hat. So you can see here, same thing as we see from the command line. I'm going to expose the service through a route just to validate through the browser that we can access the same thing. So it's available to me. Once we have seen that we can get the pods, we can get the logs for my container. Pod. You see, I've made a request, so you can see it, and I can even get into kubectl exec into my container. Why I'm showing this? Because we are going to be creating then later more containers like this one, and it's interesting to see etc nginx. We can see that this is an nginx container. We see still that there is no Docker containers, but we can see that runc lists all the containers that are running right now in my container, in my environment. So it's using runc through CRI-O, but I'm not running Docker. Okay. Whoa. Oh, I love the silence from you guys. So what if you want to run this in your laptops or anywhere? You can use Minikube. You can use OpenShift. You can use Kubernetes. You can deploy Kubernetes in the cloud. The only thing you need to do is say, hey, use this container runtime, CRI-O, and because CRI-O uses some underlying technology to make things available, it uses CNI, container native interface, container network interface to do the networking, so it has to be properly configured. So right now, I've run my containers with CRI-O. What happened with the Docker CLI? How do I, you've seen this runc list that wasn't really very friendly. It didn't tell me that much. I no longer have, if I'm gonna use CRI-O to run containers, I no longer have a CLI to interact with it. So keep calm, because there is something. There is a library called libpod, which can be integrated in a tool, and there is a CLI called Podman for managing OCI-based pods, containers, and container runtimes. This CLI is a replacement for Docker CLI, so it's just a drop-in replacement. You can use it same way as you were using Docker. You can use Podman. It will be integrated with CRI-O really soon, and there is no requirement. There is no daemon required. No daemon required. There is no daemon running. So it's just a CLI that will call and will talk to the runc runtime. You want to see it? Okay, let's go for it. Let's see. Oh. Okay. Podman PS tells you what is running, like Docker PS. And I can get the images that I have. So I have some images, and you can see that most of the images that are there are the OpenShift 3, mostly because I was running OpenShift here through CRI-O. So I have all those images available in my system. Also the nginx that we just run. So we are going to run the same nginx image that we ran before, but just as a standalone container, not right now, not integrated with Kubernetes, just as a drop-in replacement for Docker. So podman run -it nginx. When I do this, container is running. It looks like it's hung, but it's not. So let's go to a different terminal, and here I can curl. This terminal is in the same VM, so I can curl. We can see that the request went through, and I can do things like I would do in Docker. So I can PS the container. I got the same output I would get with Docker, exactly the same. I can even get the logs from my container. I can even exec into my container. I can see that is the same nginx I had before. Okay. So now that we've seen that we have run multiple containers, I'm gonna run something else. So put my images. I'm going to run with the Fedora image. Hello, Riga. Echo. So there it is. We can see that we have some container because I didn't remove this one. The one that I ran before, it was meant to be removed when I exited the container. This one is not meant to be removed when I exit the container. But Docker also allows you to build containers. So can I build containers the same way with Podman? Yes. So I have a Docker file here. This Docker file is really straightforward. I'm not a really good developer, but it just has it outputs into one file and the root directory built in Riga. Okay, so let's build this container. Let's give it a tag, Riga example, and create a Docker file. Now you are seeing more or less the same output you will see with Docker, but it's slightly different. Why? Because it's not using Docker to build a container. It's using something else that we will see in a minute. It's using one library that integrates perfectly with CRI-O, with Podman, that allows you to build OCI containers. So now I can see Podman images. I can see the image I just built. It's at the bottom, Riga example. And we can verify that the image can be run, Podman run minus IT, this one. And we're going to cut the file I just made to verify it's there. So Podman PS, I have some containers there. And one thing that we can do with Podman, one thing that Podman did is, because Docker sometimes is not flexible enough and it doesn't incorporate some of the needs developers has to delete containers with Docker, sometimes it's not so easy when you have multiple of them. So Podman introduced some new flags for some stuff, like Podman rm -all, which deletes all the containers. I'm going to show you later what is the Docker syntax, which is not so simple and trivial. Good. So we have used a replacement, a drop-in replacement for Docker. What else? Sometimes you want to move containers, you want to pull containers, you want to get containers that are built using Docker, you want to pull them to CRI-O. So there is no Docker pull, but there is some library called Scopio that allows you to copy, move, inspect, and delete containers in different image formats with different transport. So it can allow you to move OCI containers from container storage, allows you to use a directory, a Docker registry, a Docker archive, a Docker daemon locally, OCI, OS3, which is a Red Hat Enterprise atomic way of atomic Linux storage for them. And as I said, it allows you to inspect and delete images, and it's a standalone binary. There is no daemon as well running. So it's a good library that you can embed. And Podman, one of the things that it does is embedding this library to being able to pull and push images. And one really important thing where I use it quite frequently is in pipelines. One of the things that people do in Kubernetes when they have multiple Kubernetes clusters is they need to move images from one cluster to another. Like I have dev and I have production clusters, and I need to promote my image from dev to prod. How I do that? Currently, people do Docker pull, Docker push, which makes you download locally the image. It's not easy to move images from one repository or one remote registry to a different remote registry. With this, you can use this library that can allow you to move directly from one remote registry to a different registry. Want to see it again? Oh, okay. People get excited. Ooh. So let's start now Docker. Docker images. Let's verify I don't have any images, but I do have some Podman images. So one of the things that I'm going to do with CRI-O, with Scopio, is move one image from my CRI-O registry, from my local storage for CRI, OCI storage, to Docker daemon storage. So let's Scopio copy, and let's use the one that we just built. Latest, I need to specify from where. So this is containers storage. And I'm going to put it in the Docker daemon. So Docker daemon, and the same place, latest, boom. And now it's moving the image from my OCI storage to my Docker storage. Let's verify, and it's there. Let's see if I can run this image that I built using Podman. So Docker run. No, this time I'm using Docker. Let's use the image, and then let's cat the hello file I created in that. Ooh, built in Riga. So the image that I created with CRI, with the OCI, which is OCI compliant and is stored in the OCI storage, I move it to the Docker. The image, because it's compliant with the formats, can be created with one tool, can be run with a different tool. So let's delete Docker ps -a. Oh, I did delete. Okay, so the Docker is deleted, and then let's inspect. Let's inspect this image in the Docker daemon to see that Podman is also a tool for doing image inspection. And by the way, this was the initial goal of the tool, was to be able to inspect remote registries to get metadata of the images, and it grew to different use cases. Okay, so let's keep going. Ooh, I don't have time, almost. Keep calm, there is no Docker build. So remember before we did a Podman build, and we created containers. So how Podman is building, it's using a library called Buildah that allows you to build images. It can use different ways of building images, so it can use a Docker file. You can provide a Docker file and it will build a Docker file, or it can use a cell-like syntax. So that means that you can create a container, you can then access that container, like if it was your running container, install stuff like you would do normally in your VM or your laptop, and whenever you are finished, you say, hey, I'm done, this is my image, commit it, and so it's easier for you to programmatically use some tools. There has some benefits, like image, the layers can be squashed easily. So last demo of the day, if you want to see it, let's go with the... Just come and see me, I'll get you a beer this afternoon. So let me see. Let's copy Fedora-based image. I want to have also in the Docker demo, the Fedora image. So I do Docker images, and now I have a couple of images. So I go to the Docker file again. And here, what I'm going to do is, first of all, show you what's the difference. Oh, let's build the image with Docker, of course. So Docker build -t Riga sample Docker. And this one, it's using Docker to build the image. So Docker images, I have two images. So I have two images now, one in Docker that I built with Docker, one that I built with Buildah. The difference that you can see immediately by default is that if you do Docker history to the image that I built with Docker, is that every run command, every command in the Docker file creates a layer. If we look instead to the one that I created with Buildah, you see that there is only one layer because by default, Buildah does squashing of the images. This can be defined, this can be customized, but it's really useful to minimize the amount of, or the size of the images that you pull and push in environments, in cloud environments, because at the end, probably you have seen that images eventually are really, really big. So here, let's build that. Let's command for build is POD, build using Dockerfile, and then we got let's use this example. So we see that is building same way as we did before with Podman. Okay, so I'm going to show you a more nicer example. Container equals. One of the things that you can do is say, hey, Buildah, I'm going to build an image from Fedora. So this is creating me a container. So if I echo container, this is a Buildah container. So we can see there is a Buildah container. So now what I can do is add stuff to this container. So I can just do config author Jorge to this container. Let's inspect this container to see that the metadata that I just added is there. So we can see somewhere that the author is there. And we can do build run my container, and I'm gonna do a bash. So now I'm in the container. I could do in the container, I could do anything. So let's let's direct this to hello. Oh, and it's not a cat, it's an echo. So now I can exit my container and I can commit this container. So build a commit the container that I have, and let's give it a name. Riga Buildah. So we can see that there is an image there that was created. I'm gonna skip a little bit of the demo because otherwise I will run out of time. And let's keep going. There is a couple of slides more, and then some time for you to make questions. So what else? As one of the things that we have seen is that through standardizing the container format and the image format, the runtime format, Kubernetes can run multiple containers in different formats, can run them, but there is no standard way of building containers. There is no tooling for how to build containers. There is no specification that gets into how you build your containers. So there is more ways of building containers. I just showed you one, which is the one we use internally in our product and with CRI-O and Podman. But there is more. And there is even not only more tools, but different strategies. So one of the strategies is daemonless Docker files builds. So daemonless Docker files builds means that you have a Docker file, so you want to build your image with a Docker file, But these images are built without a Docker daemon. We just remove or get rid of the Docker daemon, so there is no Docker daemon, but we still want to be able to create images with a Docker file. Why? Because the Docker file build-like experience, we want to have a Docker file build like a Docker build-like experience, which is a Docker file. There is so many Docker files available. There is already so many people that knows how to do a Docker file, more or less. We want to be potentially have more control on the layers, so that's something that you can do with the tools, and you can provide greater security in these tools now that they are not using the Docker daemon. There is some benefit or some drawbacks to using this approach. So using Docker files sometimes might constrain what you can do because the syntax might be too complex, and there can be different approaches to layer construction. So there is a set of tools, Buildah, IMG, Canico, and many, many more. I just highlighted these three because these three are probably the ones that you will see in the future whenever you talk about building OCI containers. Buildah is the one I just showed. IMG is it's a library, it's a tool, it's a standalone daemonless and privileged Docker file and OCI compatible container image builder that was built by a girl, a woman, a lady named Jess Frazel. She is really a hacker. She knows how to do real cool stuff. And this technology, it's really, really good to build containers in an unprivileged way. The commands are the same as Docker, so you can just drop in, replace Docker with IMG as well. And Canico, it's a tool built by Google, and it's also a tool to create OCI container images from a Docker file, but this time inside a container or a Kubernetes cluster. So that means that eventually, and this will happen probably not so distant from now, there will be a way for building containers in Kubernetes. So you will do a build. There will be a semantic like build configuration, like the one we have in OpenShift, that will build the container images in Kubernetes cluster. And one of the benefits of Canico is that it executes each command within a Docker file completely in user space. So it's totally unprivileged. So that means that it is really secure. So you can do that anywhere, and you can create any type of build, any type of container build. And then there is the other type of approaches, which is the Docker file-less builds. This type of builds, what they try to do is you give a source code and an intention to build the source code into an artifact or an image. So for example, I want to run a Node.js web application server. So you can run a Node.js. It will build an image with a Node.js application server. Not really with a Docker file, but it will eventually create an OCI image. The pros of this approach is that it requires much less configuration. Some of the tools can intelligently or put some intelligence in the tool to build layers, to reuse and cache layers. So there is a lot of things that you can do in the tools. And you can even enforce Docker images best practices in the tools. Drawbacks, it's less flexible. So it's an opinionated way of building images, and it is very fragmented across vendors. So that means that mostly every vendor, or there is multiple ways of doing this. There is no real standard. So some of these approaches, source to image, this is the one that OpenShift does. OpenShift creates Docker containers, Docker images in the platform. So you say, hey, this is my source code. I want to build a PHP application with my source code. It will go to Git, fetch the source code, build the container, and make it available to run in the cluster. There is build packs embedded by Heroku, adopted by Cloud Foundry and Days, now Microsoft, and it's the same thing. So the user provides a source, the build produces a slug, and the export produces an image. And then there is a couple of them more, FTL, Faster Than Light, and Bazel, which are tools used by Google, both of them, although they are not really, I will say that they are not going to be relevant, in my opinion. So as you have seen, we have run containers without Docker, and some people will think that this is magic, but as you have seen, that's something that even I can do. So now time for questions. Right on time. Raise your hand if you have questions. There was a slide for that. So don't forget to tweet if you like it or if you didn't. Any question?
Thanks for the lecture. I have a question about how you build a pipelines with all these tools, so to deployment, to draw the different environments. So when you use a Kubernetes locally, afterwards you use a CRI-O.
So yeah, whatever you do to build the image, it's depending on your pipeline. So usually, for example, in OpenShift, we use Jenkins to the pipelines to execute the pipelines for container images. So you can choose how you want to build the image. You can use source to image like we do directly by talking to the OpenShift API that will create the build, and that will create the Docker image or the OCI CRI-O image. Or you can just call out to a library that will do that. So a library is Podman, so you can embed directly the Podman call within your pipeline code. One of the things that usually happens is that if you know how to build the image with your pipeline, depending on which pipeline server or CI/CD server you have, it might provide you some capabilities. One of the things that you will most likely need to use is a way for moving images from different registries. So Scopio, as I said, is a tool that you can use to move images from a registry, development registry, for example, to production registry. The image itself, you will usually use Docker or CRI-O build or Podman build to create the Docker file or the container image.
Thank you.
Any more? Okay. Thank you, everybody, for coming. And remember to tweet.